The research leverages the obstacle problem formulation from ice sheet modeling and deep learning methodologies to enhance ice thickness predictions, focusing on the Greenland ice sheet. It harmonizes the mathematical structure with an energy minimization framework tailored for neural network approximations. The efficacy is confirmed through 1D and 2D numerical simulations. The study utilizes the NSIDC 0092 dataset for Greenland and incorporates bedrock topography for model pre-training, registering notable advances in prediction accuracy. This research underscores the potent combination of traditional mathematical models and advanced computational techniques in delivering precise ice thickness estimations. The melting of ice sheets, driven by climate change, is a pressing concern that has garnered attention across various scientific disciplines. Mathematicians have developed complex models to understand ice sheet dynamics, with obstacle problems offering a unique perspective, presenting challenges in partial differential equations. Numerical methods, such as the Galerkin least squares finite element method, multigrid algorithm, and piecewise linear iterative algorithm, have been devised to address these challenges, primarily focusing on providing approximation solutions to the weak variational inequality. In recent years, deep learning has emerged as a promising tool in scientific applications, including solving differential equations and inverse problems. Despite its growing popularity, its application to variational inequalities remains in its infancy. Some studies have applied deep learning to traditional obstacle problems, while others have explored deep learning techniques for elliptic hemi-variational inequalities. However, a common limitation of these studies is that they often prioritize computations over theoretical insights. This paper aims to bridge this gap by exploring both traditional ice sheet models and introducing a computational approach using deep learning to address the obstacle problem, drawing inspiration from its variational form. A key focus of this work is to investigate the influence of parameters such as network size and training samples on the outcomes. Through rigorous numerical experiments, the paper substantiates the effectiveness of this approach in estimating ice thickness. The mathematical formulation of the model, adapted from previous studies, defines a domain omega within R2 as a bounded and connected open subset with a Lipschitz continuous boundary. The bedrock elevation is represented by the function b, where positive values indicate elevations above sea level and negative values represent depths below it. The top surface elevation of the ice sheet, denoted as h, always maintains a value greater than or equal to b throughout the domain omega. This relationship is visualized in Figure 1. The thickness of the ice, h, is consistently non-negative throughout omega, making it an obstacle problem where the bedrock acts as the primary constraint. This constraint implies the existence of a free boundary, defined as omega plus, where h greater than 0. The cross-sectional view of an ice sheet, as presented in Figure 1, illustrates the notation used to describe the region where ice is present, denoted by omega. The free boundary, gamma f, is defined as the intersection of omega and its boundary, partial differential omega plus. The source function a, representing ice accumulation or ablation, is expected to be positive within omega plus, indicating ice accumulation, and negative outside omega plus, indicating ablation, especially within omega minus, the complement of omega plus and gamma. This dynamic process causes the ice to migrate from accumulation zones to ablation zones, resulting in the ice sheet tapering to a negligible thickness at its edges. The basal sliding velocity, UB, is a vector field in R2 that depends solely on the lateral position and is 0 when the ice base is in a frozen state, as documented in reference 9. The horizontal ice flow velocity is represented by the vector field u, which can be computed using the surface elevation and its gradient, as discussed in 9. The viscosity of the ice is described by the Glenn power law, with an ice softness coefficient A, x, z, and an exponent p, which ranges from 2.8 to 5, as suggested by laboratory experiments, 5. The Glenn power law is used to model the nonlinear relationship between the ice velocity and the stress applied to the ice. In the realm of ice sheet modeling, a mathematical framework has been developed to simulate the surface elevation and velocity of an ice sheet. The surface elevation is determined by a nonlinear partial differential equation, which considers the ice's density, gravitational acceleration, and the mass balance data. This equation correlates the ice surface's motion with the ice velocity and mass balance data, where the volume flux is characterized by a vector field q. This vector field is defined as the integral of the ice flow velocity concerning the vertical direction. By incorporating the surface equation and the volume flux into the continuity equation, the equation for surface elevation h can be formulated. For scenarios where the ice's flow law coefficient a, x, z remains constant, the equation simplifies to a form that includes a positive constant k to form a weak solution for this problem over the entire domain. It is necessary to assume the absence of a volumetric ice flow towards the domain's boundary. This leads to the extrapolation of the volume flux q as zero outside the domain containing ice. This mathematical framework provides a foundation for understanding and predicting the dynamics of ice sheets, which is crucial for climate change research and understanding future impacts on global sea levels. The authors introduce a smooth test function, VAS, which satisfies v is greater than or equal to b throughout the domain omega, and multiply equation 5 by vh, subsequently integrating over omega. By applying Gauss's theorem, they derive an inequality, equation 10, which, after some manipulations, yields equation 11. This equation is then rewritten in terms of q, using equation 7, resulting in the variational inequality 12. A crucial observation is that q exhibits degenerate behavior at the free boundary. To address this, the authors employ a transformation, introduced in reference 3, which replaces u with h, as defined in equation 13. This transformation leads to a reformulated version of equation 7, given by equation 14, where micro, x, u, and phi, x, u, are specific functions. In the present work, the authors focus on simplifying the nonlinear dynamics by making specific assumptions to address a more tractable problem. Specifically, they consider the scenario where UB equals 0, which allows them to set psi, x, u, equals 0 and treat micro, x, u, as a constant, denoted micro 0. Under these assumptions, the inequality in equation 12 simplifies to equation 15. The author's approach involves applying Gauss's theorem to derive a variational inequality, which is then transformed to address the degenerate behavior at the free boundary. By making specific assumptions, they simplify the nonlinear dynamics, leading to a more tractable problem, as expressed in equation 15. The inequality holds for all v is greater than or equal to 0 defined over omega and p is greater than or equal to 2, with micro 0 equals 1 for simplification purposes. This study builds upon the foundational work of the original authors, delving deeper into the n-nonlinearities inherent in the problem. Two primary n-nonlinearities are examined: the PLA place-type nonlinearity resulting from Glenn's flow law, and the nonlinearity introduced by the bedrock gradient, nabla b, in phi, x, u. The original authors only considered the simplified case of p equals 2, whereas this research explores the complexities of the PLA place-type nonlinearity for p greater than 2. The bedrock gradient nonlinearity is introduced in scenarios where the bedrock elevation is not flat, adding an additional layer of complexity. By addressing these n-nonlinearities, this study aims to provide a more comprehensive understanding of the problem, shedding light on previously overlooked aspects. The approach taken explicitly addresses these n-nonlinearities, offering insights and solutions that build upon, augment, and enhance the foundation set by the original authors, particularly as the formulation transitions into energy minimization. The energy minimization formulation is based on a Hilbert space V, such that V element of H, omega. A subspace U is defined as the set of all V element of V such that V equals 0 on partial differential omega. The constraint set K is introduced as the set of all V element of V such that V is greater than or equal to B in omega and V equals 0 on partial differential omega. The paper introduces a variational inequality problem, repositioned as an energy minimization problem. The objective is to find a function u within a certain space K such that the energy functional J, u, is less than or equal to J, V, for all V in K. This energy functional is defined by J, V, equals B, V, V, less than A, B greater than, where B, V, V is a specific integral term involving the gradient of V and a given function psi. To solve this problem, the authors introduce a regularization term to the energy functional, creating an augmented energy functional L, V. This augmented functional includes a penalty term that measures the difference between the solution V and a given function B. The solution U of this regularized problem approaches the solution of the original problem as the regularization parameter alpha increases. The authors then formulate a minimization problem to find the function versus that minimizes the augmented energy functional L, V. This functional is defined by an integral term involving the gradient of V, the function A, and the penalty term. In numerical computations, this continuous energy functional is approximated by its discrete counterpart, which involves summing over a set of points in the domain. This approach allows for the solution of the variational inequality problem through energy minimization, with the introduction of a regularization term to improve the numerical stability and convergence of the solution. The discrete approximation of the energy functional facilitates practical computations and provides a means to approximate the continuous solution. The minimization problem is addressed by introducing a modified energy functional, which includes terms for the solution on the boundary and its deviation from a given boundary condition. This functional is then used to seek efficient computational methods, where deep neural networks, DNNs, are identified as a promising tool due to their ability to capture nonlinear relationships. A fully connected feedforward neural network is used to approximate the solution, with the network's weights and biases refined using backpropagation based on a loss function derived from the energy minimization formulation. The network's performance is evaluated using a composite loss function, consisting of residual loss, which measures the difference between the network's output and the target solution. The novel neural network-based method for solving partial differential equations, PDEs, with obstacles and boundary conditions involves a three-component loss function. The first component, PDE loss, measures how well the network approximates the solution of the PDE through mean squared error of the residual. The second component, obstacle loss, ensures the resulting solution lies above the constraint by minimizing the squared difference between the network's output and the obstacle function. The third component, boundary condition loss, adheres to known values on the domain's boundary by minimizing the squared difference between the network's output and the prescribed boundary conditions. The total loss function is a weighted combination of these three losses, with coefficients alpha and beta balancing PDE satisfaction, constraint satisfaction, and boundary condition satisfaction. The authors employ a batch approach for training, refining the network parameters iteratively. This foundation sets the stage for exploring the neural network's practical applications in solving complex PDE problems. The authors describe the sequence of numerical experiments to be performed, starting with the method of manufactured solutions, MMS, to test the deep learning approach. This technique involves creating an exact solution for an augmented form of the partial differential equation, PDE, by choosing a solution function that satisfies obstacle and boundary constraints, computing the residual, and augmenting the PDE with an inhomogeneity that offsets the residual exactly. The manufactured solution serves as a ground truth for rigorous comparison with numerical approximations. The authors aim to validate the robustness and accuracy of the deep learning approach by applying MMS to a simpler PDE with an obstacle constraint, followed by the more complex PDE of interest with the constraint, on both 1D and 2D domains. Subsequently, the approach will be tested on the motivating problem of finding the elevation profile of ice above the bedrock of Greenland. The solution approximator architecture consists of a minimum of 5 hidden layers, each with 128 neurons, utilizing the squared rectified linear unit, ReLU2, to leverage its improved differentiability and empirical performance. Layer normalization techniques are integrated to foster a consistent learning environment. The optimization phase employs the atom variant of stochastic gradient descent, SGD, with a learning rate schedule determined through trial and error, aiming to minimize the associated loss function. The implementation and training processes rely on the capabilities offered by the TensorFlow framework. Researchers explored the feasibility of utilizing the PyTorch library for a specific network and training structure, focusing on a unidimensional problem with p equals 2. In this context, an obstacle function b, x, is employed, which varies across different intervals. Notably, the exact solution for this problem is provided, offering a benchmark for comparison. Figure 2 presents a visualization of the 1D solution, obstacle function, and exact solution, facilitating a comprehensive understanding of the problem's dynamics. This numerical exploration serves as a foundation for future refinements, laying the groundwork for more in-depth studies. By leveraging PyTorch in this context, the study demonstrates the potential for efficient and accurate solutions to complex problems. The training process for the solution approximator involves modifications tailored to the specific problem. Points for evaluation are drawn from a uniform distribution over 0, 1. The neural network undergoes training over 2,000 iterations with the regularization parameters alpha and beta fixed at 4,000. The performance is assessed on a mesh grid with a fine resolution of 10 to the power of 3. The numerical solution is presented in Figure 2, alongside the obstacle function and the exact solution. Figure 3 charts the evolution of loss metrics, showing the efficiency of the proposed technique, which typically converges within 500 iterations. The evolution of different losses during training is illustrated in the figure, with a logarithmic scale on the z-axis representing the number of iterations. The total loss, computed from equation 26, symbolizes the overall loss value. The residual loss term, derived from equation 23, highlights the residual error inherent in the approximation process. The obstacle loss term, weighted by coefficient alpha, encapsulates the loss due to obstacles within the problem domain, as defined in equation 24. The boundary loss term, accentuated by coefficient beta, highlights the loss inherent in the problem boundaries, as per equation 25. The difference between the exact and approximated solutions is quantified using the L1 norm, providing insight into the convergence and accuracy of the approximation method. The accuracy of a neural network approximator in solving partial differential equations, PDEs, is significantly impacted by the sampling granularity. The choice of sample points for computing the PDE loss can influence the convergence behavior and accuracy of the neural network's predictions. Figure 4 illustrates the evolution of the L1 error between the approximated solution U** operator and the exact solution U exact over training iterations, demonstrating the difference in magnitudes as training progresses. This showcases the convergence and accuracy of the neural network's predictions. A systematic analysis of sample size and resultant relative error, presented in Figure 5, provides insights into how the sampling granularity can influence the accuracy of the derived solution. The sample points are chosen from a uniform grid to ensure a consistent and unbiased assessment. The study highlights the importance of sampling strategy in neural network-based PDE solvers, emphasizing the need for careful consideration of sampling granularity to achieve optimal results. The analysis on this page examines the relationship between the number of samples and the relative error. Figure 5 illustrates this relationship, demonstrating a decrease in relative error as the sample count increases. A regression line with a slope of 0.83 is superimposed on the plot to visualize the expected linear scaling of error with the number of points. This slope falls between the theoretical expectations of 1 and 1/2. Indicating that the error reduction behavior is intermediate between these two expectations. The results suggest that errors decay faster than 1 sqrt, n, but more slowly than 1 n for the range used. The analysis on page 17 explores the impact of sampling, regularization parameters, and loss weighting on relative error, emphasizing the importance of balancing these parameters to avoid overfitting or underfitting. Table 1 illustrates the relative errors for various regularization parameters, highlighting the need for a proper balance. The section then shifts focus to the 2D problem with p is greater than or equal to 2, using a circularly symmetric obstacle function. It constructs an exact solution within the domain 0, 1 times 0, 1, demonstrating the approach's applicability to more complex scenarios. The exact solution, denoted by U exact, is defined as a piecewise function of R, with different expressions for R less than or equal to R** operator and R greater than R** operator. For R less than or equal to R** operator, U exact is defined as 1 minus the difference between f of R and g of R, plus 1 minus e of R. For R greater than R** operator, U exact is a combination of terms involving r operator, and p, ensuring C1 smoothness. F, G, and E are auxiliary functions defined as Rp to the power of p minus 1, 1 minus r to the power of p minus 1, and p to the power of p minus 1 times r, respectively. The exact solution, obstacle function, and neural network approximation are visualized in Figure 6 for p equals 3. The obstacle function plot, exact solution plot, and approximated solution plot demonstrate the effectiveness of the neural network in approximating the exact solution. In this study, the weighting parameters alpha and beta are set to 100, and the network is trained for 2000 iterations. The losses are plotted on a logarithmic scale against the number of iterations, illustrating the efficiency of the training process. Additionally, the L1 norm of the difference between the approximated and true solutions is shown as a function of training iteration, further highlighting the convergence of the neural network to the exact solution. The figure illustrates the evolution of different losses during training, plotted on a log scale against the number of iterations. It shows the dynamics of 4 losses: total loss, loss 1, loss 2, and loss 3. Each loss corresponds to a specific equation in the paper: equation 26 for total loss, equation 23 for loss 1, equation 24 for loss 2, and equation 25 for loss 3. This visualization provides insight into how these losses change throughout the training process, highlighting the impact of coefficients alpha and beta on loss 2 and loss 3, respectively. The evolution of the L1 error for a parameter setting p equals 3 is analyzed, providing insights into the neural network's convergence behavior and prediction accuracy. A visual representation of the obstacle function, exact solution, and the neural network's approximation for p equals 4 is presented in Figure 9. This figure demonstrates the methodology's effectiveness by plotting the obstacle function, exact solution, and the approximated solution. The results highlight the neural network's ability to approximate complex solutions accurately, which is crucial for solving variational inequalities and obstacle problems efficiently. This section contributes to the overall understanding of the paper's novel approach to solving these problems using deep learning techniques, showcasing its potential in fields such as computer vision, robotics, and engineering. In the post-training analysis of the neural network's approximation for p equals 4, visual comparisons and efficiency assessments are conducted. A comprehensive visual comparison is provided by juxtaposing the exact solution and the neural network's approximation, as shown in Figure 9. The loss behavior during training for p equals 4 is examined in Figure 10, where different losses are plotted against the number of iterations on a log scale. Specifically, the total loss, loss 1, loss 2 influenced by coefficient alpha, and loss 3 affected by coefficient beta are considered, as defined in equations 26, 23, 24, and 25, respectively. The L1 error is computed to assess the efficiency of the neural network's predictions for p equals 4, as illustrated in Figure 11. This analysis provides a detailed evaluation of the neural network's performance in approximating the solution for p equals 4, highlighting its strengths and weaknesses. The convergence and prediction accuracy of the approximated solution U** operator compared to the exact solution U exact over iterations are illustrated in Figure 11, demonstrating the efficacy of the proposed approach in approximating the obstacle-constrained ice sheet PDE in simplified 1D and 2D domains. The authors then apply this approach to a realistic obstacle geometry using the Greenland bedrock elevation dataset from the National Snow and Ice Data Center, NSIDC. This dataset, specifically the NSIDC 0092 dataset, provides comprehensive information on Greenland's ice melt and movement, including ice thickness, digital elevation models, DEMS, and bedrock elevation data. The parameter range of this dataset is extensive, with DEM values ranging from 0.1 meters to 3,278.3 meters, ice thickness measurements from 0 meters to 3,366.5 meters, and bedrock elevation data varying between 963.1 meters and 3,239.0 meters. The application of the proposed approach to this dataset offers a rigorous testbed to evaluate the adaptability and robustness of the algorithms, aiming to demonstrate the effectiveness in solving the obstacle-constrained ice sheet (PDE) in a realistic and complex domain, highlighting its potential for real-world applications in glaciology and climate modeling. The dataset used in this study is organized into ASCII text grids with a spatial resolution of 5 kilometers, comprising 301 columns by 561 rows. This grid resolution ensures a comprehensive and granular view of the ice sheet and bedrock topography across Greenland, suitable for precise climatological and glaciological analyses. The dataset's utility in modeling and analyzing the dynamics of Greenland's ice sheet and underlying bedrock is highlighted by its 5 km grid resolution. To provide context, we begin by visualizing the bedrock topography from the dataset, as shown in Figure 12. This representation serves as our obstacle function for the subsequent analysis. The bedrock topography of Greenland derived from the NSIDC 0092 dataset is crucial for understanding the complex interactions between the ice sheet and underlying bedrock, essential for climate change research and ice sheet dynamics modeling. Approximating bedrock elevation from Greenland's ice thickness data using neural networks is hindered by challenges associated with conventional random initialization. To overcome these limitations, a two-stage modeling approach is proposed. In the first stage, the neural network is intelligently initialized by training it to mimic the bedrock elevation, as shown in Figure 12. This preliminary training phase enables the network to learn and approximate the patterns of the bedrock topography. This initialization method is not a solution to the problem but rather a means of priming the network for subsequent training. In the second stage, the initialized network is trained to approximate the partial differential equation, PDE, following the same method as previously described. This approach aims to mitigate the high error rates and unpredictable behavior observed with conventional random initialization. By leveraging this two-stage methodology, the authors seek to improve the accuracy and reliability of bedrock elevation approximations from Greenland's ice thickness data. The neural network is pre-trained on bedrock elevation data, a crucial step in achieving efficient learning and error reduction. This process involves optimizing the network's weights, which are then used as initialization parameters for a second phase of training. The training setup, including penalty parameters and the network architecture, is detailed to provide a comprehensive understanding. The training process consists of a total of 1,000 iterations, emphasizing the importance of accurate convergence. Researchers have developed a neural network to approximate ice thickness, leveraging the NSIDC 0092 dataset for training and validation. This approach enables a comparison between the neural network-derived approximation and precise ice thickness data over Greenland, as visualized in Figure 14. Notably, direct interpretation of training losses is challenging, prompting an alternative strategy. By analyzing the properties of the neural network solution alongside ice sheet thickness data, the study assesses how well the approximation satisfies the underlying partial differential equation, PDE, without relying on direct solution data comparisons. This novel approach facilitates a more nuanced understanding of the neural network's performance, highlighting its ability to capture complex ice thickness patterns while minimizing errors. The results demonstrate the potential of neural networks in approximating ice thickness, with implications for improved climate modeling and glacier dynamics research. The authors conduct a comparative analysis of their model's performance in approximating the solution to the PDE for ice sheet thickness, using a benchmark for comparison. They compute the losses that would be found from inserting the measured ice sheet data into the three loss terms, which form the dashed lines against which training losses are compared in Figures 15 and 16. Figure 15 shows the trajectory of the losses as a function of training iteration for p equals 3, indicating that all losses converge to an absolute level consistent with the real ice sheet thickness data's satisfaction of the PDE. This, combined with the visual comparison of the approximated solution to the real data, suggests this approach well approximates the solution to this PDE. Similar analysis was carried out for p equals 4 with similar results in Figures 16. The analysis demonstrates the effectiveness of the proposed methodology in approximating the solution to the PDE, highlighting the potential of using deep learning techniques to solve complex partial differential equations in geophysics. The paper integrates mathematical modeling and deep learning to understand the dynamics of the Greenland ice sheet. It establishes a robust theoretical framework based on variational inequalities and obstacle problems, leveraging neural networks for solutions. A key aspect is pre-training, where the neural network is first familiarized with bedrock topography, optimizing the learning process when actual ice thickness data is introduced. This approach underscores the importance of judicious model initialization. Researchers have successfully merged deep learning techniques with mathematical models to investigate the dynamics of Greenland's ice sheet. By applying this novel approach to the NSIDC 0092 dataset, the method achieved remarkable accuracy, closely replicating the exact data. This interdisciplinary fusion of machine learning and mathematical modeling holds significant potential for climate science, particularly in understanding the melting of Greenland's ice sheet and its far-reaching global implications. The study showcases the benefits of combining deep learning and mathematical models, yielding efficient computational methods that can be adapted to other domains. This integration enables the creation of more accurate and efficient models, capable of capturing complex interactions within the ice sheet. The resulting models can provide critical insights into the ice sheet's dynamics, informing predictions of sea level rise and climate change. The approach's accuracy is attributed to its ability to capture nonlinear relationships between variables, a limitation of traditional mathematical models. The deep learning component learns patterns in the data, which are then incorporated into the mathematical models, enhancing their predictive capabilities. This synergy enables the creation of more robust and reliable models, capable of simulating the ice sheet's behavior under various climate scenarios. The study's findings have significant implications for climate science, offering a novel framework for investigating complex Earth systems. The approach can be extended to other domains, such as glacier dynamics, sea level rise, and climate modeling, providing a powerful tool for understanding and predicting the impacts of climate change. Deep neural network-based method for solving obstacle problems. Research in obstacle problems has seen significant advancements, particularly in the application of deep neural networks. This approach leverages the power of deep learning to solve variational problems, providing an efficient and accurate numerical algorithm known as the deep RITS method. This method is particularly useful for solving partial differential equations, PDEs, that arise in various fields such as physics, engineering, and finance. First-order least squares method. Another numerical method used for solving obstacle problems is the first-order least squares method. This approach is based on minimizing the least squares functional of the residual of the PDE, which can be expressed as a quadratic form involving the gradient of the solution. This method has been applied to various problems, including those related to ice sheet dynamics. Deep RITS method. The deep RITS method is a deep learning-based numerical algorithm for solving variational problems. It uses neural networks to approximate the solution of the variational problem, which can be expressed as a minimization problem involving a certain energy functional. This method has been successfully applied to solve various types of PDEs and has shown promising results in terms of accuracy and efficiency. Monte Carlo methods in financial engineering. Monte Carlo methods are widely used in financial engineering for pricing derivatives and assessing risk. These methods involve generating multiple scenarios of asset prices over time and calculating the expected value of the derivative based on these scenarios. Monte Carlo methods are particularly useful for complex derivatives where analytical solutions are not available. Galerkin, least squares finite element methods. The Galerkin, least squares finite element method is a numerical technique used to solve the reduced wave equation. This method combines the Galerkin method, which is based on the principle of weighted residuals, with the least squares method, which minimizes the residual of the PDE. This approach has been applied to various problems in physics and engineering. Adaptive learning on grids for elliptic hemivariational inequalities. Adaptive learning on grids is a numerical method used to solve elliptic hemivariational inequalities. These inequalities involve both linear and nonlinear terms and are commonly encountered in mechanics, physics, and engineering. The adaptive learning approach involves dynamically adjusting the grid size and shape based on the solution to improve accuracy and efficiency. Neural networks for forward and inverse scattering problems. Neural networks have also been used to solve forward and inverse scattering problems. Forward scattering problems involve predicting the scattered field given the incident field and the properties of the scatterer. Inverse scattering problems, on the other hand, involve determining the properties of the scatterer given the scattered and incident fields. Neural networks can be trained to approximate the solution of these problems, providing a fast and accurate numerical method. The study of variational inequalities and their applications has seen significant contributions from various research papers. David Kinderlehrer and Guido Stampacchia introduced the concept of variational inequalities, laying the foundation for future investigations. R. Kornhuber's work on monotone multigrid methods further advanced the field, providing a new approach to solving these complex problems. In addition, K. Mayava and X. C. Tai explored the use of level set methods, offering a novel perspective on the numerical solution of partial differential equations. Meanwhile, Adam Poschke et al. Demonstrated the potential of PyTorch in deep learning, showcasing its versatility and efficiency in handling complex neural networks. Paolo Piersanti and Roger Temam delved into the dynamics of grounded shallow ice sheets, shedding light on the intricate processes that govern their behavior. Moreover, M. Raci, P. Perdicaris, and G. E. Karniadakis introduced physics-informed neural networks, which leverage both physical laws and machine learning techniques to solve forward and inverse problems involving nonlinear partial differential equations. The obstacle problem, a fundamental challenge in variational inequalities, was addressed by J. F. Rodriguez, Xiaoliang Ran, Qinghua Cheng, and Stefan Abide. Their research provided new insights into the mathematical and numerical aspects of this problem, paving the way for more efficient solutions. Finally, Samuel H. Rudy, J. Nathan Kutz, and Stephen L. Brunton demonstrated the power of deep learning in signal noise decomposition, illustrating how these techniques can be used to separate meaningful signals from background noise in complex datasets. Numerical methods for solving partial differential equations and uncertainty quantification have been extensively explored in various research papers. Building upon John C. Streichwerda's work on finite difference schemes, the importance of accurate numerical methods is underscored. Recently, deep learning-based approaches have emerged as a promising solution for uncertainty quantification. For instance, Rohit K. Tripathi and Elias Bilonis have demonstrated the efficacy of deep neural networks in solving high-dimensional uncertainty quantification problems. Similarly, Nick Winovich, Kartik Ramani, and Guang Lin have applied deep learning techniques to tackle complex uncertainty quantification challenges. These innovative approaches leverage the capabilities of deep neural networks to approximate complex probability distributions, enabling the solution of high-dimensional problems that are intractable using traditional methods. By harnessing the power of deep learning, researchers can efficiently quantify uncertainty in complex systems, facilitating the development of robust and reliable models. The integration of deep learning-based methods with traditional numerical techniques has the potential to revolutionize the field of uncertainty quantification. As researchers continue to push the boundaries of this emerging field, it is essential to address the limitations and challenges associated with these approaches, including the need for large datasets and the risk of overfitting. Future work in this area will focus on developing more efficient and accurate deep learning-based methods for uncertainty quantification, as well as exploring their applications in various domains. By advancing our understanding of these complex methods, researchers can unlock new insights and drive innovation in fields such as physics, engineering, and computer science.